So hello everyone. In this lecture, we will discuss one question of your previous year question of your aerospace engineering of axial flow compressor. So this question was asked in 2022 for aerospace for 2 marks. Okay, and this was your NAT question. Okay, so and we will try to understand what is the isentropic process in this, and slightly this time they have increased the level of numerical because they have introduced the this work coefficient. Previously they have not asking from this coefficients. We have a different kind of design parameter. These are the very important design parameter like work coefficient, flow coefficient, speed ratio. We have this kind of things which are the very important design condition for your compressor design for each stage. Okay, so let's discuss this question and we'll try to break down this question. Okay, yes. So okay, now let's read the question. So a multi-stage axial flow compressor takes in air at a 1 atm and 300 Kelvin and compresses it to the minimum 5 atm. Okay, so they are compressing from 1 atm to 5 atm. Compressor compressing the air from 5 to 1 to 5 atm. The min blade speed is 245 and work coefficient. This is we will discuss what is this work coefficient and what is this which is 0.55 for each stage they have given. For air they have given some gas values, universal gas constant, Cp value, gamma value. Okay, but you need to careful about this unit they have, what unit they have given, so be careful with that. Maybe you can do mistake while using Cp value for work for finding specific work. Okay, so okay, let's see. If the compression is isentropic, the number of stage required, and they have said rounded off to the next higher integer. So this was the NAT question. Okay, so let's discuss. Let's first write the what data they have given. Okay, then we will try to solve this. Okay, given data, if you see, so this was the multi-stage axial flow compressor, and that in that your stagnation pressure at the entry. Okay, let me draw the diagram of your compressor, then let me mark the station numbers, then we will try to understand. Okay, so if you see this kind of compressor we have, right, area decreases in the flow direction, right, and which is connected to your shaft rotate with the help of turbine, right. So this is your axial flow compressor. So this station number and this station number, so this one station number is not one station number at the entry, and at the exit we have not two. So depending on that we will mark the station number. So P01, which is the entry of your compressor with 1 atm, and temperature which is entering or temperature which is generating from the turbine, this is not this is stagnation temperature. Okay, we will discuss what is this. This is related to your work. Okay, so it is 300 Kelvin, and compressor it compresses it to the minimum of 5 atm. That means P02 they have also given, which is 5 atm. Okay, and now if you see they have given mean blade speed. That means your which is minimum mean blade speed, mean height blade speed, which is given by 245 meter per second. So if you see you have a different height speed. Okay, let's say this is your blade and connected to, let's say, hub or shaft as of now. So what so this is, let's say, this is 1 and this is 2 and this is 3. Okay, so this is your hub, this we say hub, this we say at the mean position, at the middle one we say it is a mean height of the blade, or this is a hub of the blade, and this is the tip of the blade. And we sometimes we say this is also say we root. Okay, so at the different height you will have a different speed. Okay, which is dictated by your, this is u root, u mean and ut, which is this is dictated by your, let's say if I taking a u mean, So this formula we have. So diameter depends on your height. Okay, so depending on that, your this mean blade speed will change. Let's say you are taking at the tip, that means you have a highest speed at the tip. At the mean you will have following that lower than at the tip. At the root or hub you will have a different speed. Okay, so I hope you understand. This is not the part of discussion for as of now. Just the that word came, so I explained that. Okay, let's discuss what they have given in the question itself. Okay, so they have given u mean, then they have given the work coefficient. So work coefficient is denoted by this psi sometime. In the question they have given this kind of notation, if you see carefully, which is given by 0.55, right? So this work coefficient, sometimes we say loading coefficient or blade loading coefficient, and this is the very important parameter of your compressor design. Okay, so if you go through any book you will find this, what is this work coefficient. And CP they have given, which is 1005. I'm not writing the unit, you know, this is joules per kg Kelvin. And R they have given it is a 287, and gamma they have given for 1.4. They have said for air. Okay, okay, so they have given this thing. If they have not given, you have to remember all this value. Default you should use air, because compressor faces the air, not gases, so you should the air property. Okay, fine. Now they are asked, now they are saying your compression process is isentropic, right? Compression process is isentropic. The number of stage required is, now if you see, let me draw the TS plot for this compressor. This is T, this is S, which is entropy and temperature, right? Let's say this is your entry of the compressor, which is not 1. So this line is a pressure line, which is at the station number or at the entry. And if you see, this is your higher pressure line, which is P02, which is always greater than P01. Okay, so what happens, this is your polytropic process. Okay, polytropic process. And if you see, if you draw the straight line, this is your isentropic process. So this becomes P0, this becomes your T02, and this becomes your T02 dash, and this is T01. So if you see, this is your isentropic process and this is your polytropic process. So in the polytropic process, what happens, your entropy increases, so it becomes your actual process inside the compressor. And isentropic process, if you see, that means you are not considering any losses, or that means you are not bothering about the you're not bothering about the entropy generation. So I hope you know entropy generation is bad. Okay, I hope you understand. The corresponding lines are temperature lines in this. This is T01, T02 dash, and this higher one is T02. So okay, I hope you understand. Okay, let's focus on the question itself. So they are asking how much how much stage we required for this much pressure generation, right? We want 5 pressure ratio at the end of the multi-stage of compressor, right? So now we required 5 atm at the exit of compressor. So how much they are asking, how much compressor stage is required. Okay, now if you see, the number of stage is given by change in temperature of your complete compressor divided by change in temperature of your stage per stage. Okay, so from here you can easily find out the number of stage. Okay, I hope you understand. So this number is always lesser, this number is always higher, so mark this is a very important. Many times they have asked how to calculate the number of stage. So okay, so now our task is just to calculate change in temperature across your whole compressor and change in temperature across stage. So we will if you get this, we can divide both. and we can get easily change in temperature, right? Okay, we can get the number of stage. Fine. So now our motive is to find, first we will find change in temperature across the stage. So if you see carefully, they have given the work coefficient, right? Work coefficient is, they have given this, and ideally from the formula, the work coefficient is nothing but u into CT2 minus CT1. So they have given C theta, right? So that theta is a tangential component or swirl or whirl component of your velocity triangle. So they have given the change, right? The delta they have given, right? So this is change in your swirl or whirl component or tangential component, and u is already present in that, and this is u square. So if you uh, take out this, so this becomes your CT2 minus CT1 divided by u, right, which is given 0.55, right? So if you calculate this from here, CT2 minus CT1, if you multiply u from the right hand side, you will get this as a 134.75 meter per second. So this is nothing but your velocities, right? I'm not going into the velocity triangle as of now. Okay, now in this formula, if you multiply u, this becomes your specific work. I hope you know that. If you don't know, you can just go through the formulas. What formula u we have? So just we need to multiply again 243. This is u mean, right? So in the question they have only given about the u mean or mean blade height, so we are only using that. Okay, this is nothing but 245, right? Again you have to multiply that. If you multiply this, you will get this 33013.75 joules per kg. So anything which is independent of mass is specific work, right? It is a specific property. So this is your specific work of your compression, required to your compression. Okay, now if you see this, work is also denoted by Cp change in temperature, which is T02 divided minus T01. So what we have to do, we will divide this work divided by C. We will divide this work with the help of Cp. So what we will get, we will directly get change in temperature across complete compressor. Okay, I hope you understand. You got this. So if you divide this, divided by 1005, you will get this as a 32.849 Kelvin. So this is change in temperature, stagnation temperature. Whenever I'm saying temperature, that is stagnation temperature for our compression. Okay, so this is your so from your each stage you are getting 32.849 Kelvin temperature. So this 32.849 will be uniform across all these stages. It cannot be different. If it is different, then your design of compressor is bad. Okay, now what we need to do, we just need to find out this across whole compressor. Oh sorry, this was your stage, this was your first stage, pardon me for that, this was for your stage. Now we need to find out change in temperature across complete compressor. So if you see, they have given the, if the compression process is isentropic. So if you remember that isentropic process is given by this formula, T02 divided by T01, P02 divided by P01 raised to gamma minus 1 by gamma. If you don't know, just remember this or plug this formula. This is a very important formula for solving your compressor. So what we can do from here, you can directly calculate T02 from here, because you know T01 and P02 by P01 you already know. This is your compressor pressure ratio, right? This is nothing but your compressor pressure ratio. So you using isentropic relation, because they have said the process is isentropic, right? So we need not to consider any losses, and you can directly use the isentropic formula, and you can calculate T02 from here, which is 475.146 Kelvin. I'm getting this 475.146 Kelvin. So now it's easy for us, I think, because change in temperature across complete compressor we can easily calculate, because we know T02, right? And T01 we already know, which is your 300 Kelvin. So if you calculate this, if you substitute and calculate this, you will get this as a 175.146 Kelvin, which is your change in temperature across complete compressor, right? Now we need to calculate the number of stage, which is given by change in temperature in complete compressor divided by change in temperature in stage. So you know that 175 of your complete compressor, and for stage we have a 32.849. just divide this, you will get this as a 5.33. now if you see, now you got number of stages of 5.33. this is not possible, right? 5.33, how you can design that? It should be otherwise it should be 5, or otherwise it should be 6, right? You cannot design 5.33 stage. This is not at all possible. So now they have said rounded off to the highest next highest integer. That means they have said next highest integer, rounded off to the next highest integer. So what it will be? It will be 6 only, right? You can either design 5 stage, or you can either design 6. So this becomes your answer. 6 becomes your answer. That means for getting the 5 atm at the exit, 5 atm pressure at the exit, you need, that means if you want compressor pressure ratio as a 5, you need 6 number of stage depending on this all given value. So you need 6 number of stage for this, and fit this value in your answer sheet as a 6. You will get 2 marks in your exam. So I hope you got this. I have done in the lengthy way to explain each and every term in that, so that you can understand. You can do you have to do this this numerical was for 1 minute only. If you are very good enough of your compressor, you can only do in a 1 minute, not a big deal, right? So okay, let's meet in a next lecture. You can also match this this answer. This is nothing but given here, greater than or equals to 6, and this was for 2 marks, and this was NAT. Okay, question number 65. So let's meet in the next lecture. Okay, if you have any doubt, you can ask me in the comment section. I will try to clear this. Thank you.